Okay, let's move into the topic of evaluating classification models. So of course, we have a broad idea that the way in which we evaluate the models is that we divide the data into training and test. We build a model on training and then we evaluate it on the test. Now we are getting into more details about what do we mean by evaluating a classification model on the test partition. Okay, so we are going to learn a number of classification techniques. So for example, classification trees, k nearest neighbors, naive Bayes, logistic regression, neural networks. These are all different techniques for classification that we are going to learn. Maybe a couple more too. Okay, but at this point, I'm not going to talk about any of these techniques. By at this point, I mean right now in this week's lecture, right? Subsequent weeks, we will devote a week or more to each of these techniques separately. Okay, so right now, what I want to talk about is things that are common to all classification models. That is, the way in which we evaluate the classification models is the same, irrespective of what kind of classification models we build. Okay, so right now I'm going to pretend as if classification models are already available and we'll only look at how to evaluate them. Okay, I'm doing that because that process is common to all of them. Okay, so for now, don't worry about how each of these models actually works. We're going to devote a lot of time to understanding specifics of those things. For now, just assume that somehow, yes, there's a black box. It does classification. All we are worried about is how good is it? How are we going to evaluate it? Okay, so again, we just come back to our good old idea of historical data. Let's say we've got 10,000 rows. Of course, since it's historical data, we've got the values for all the predictor attributes and the target attributes. And as you already know, we are going to partition the data into training partition, test partition. A typical breakup between training and test is 70% in training and 30% in test, but you can vary it. I mean, this is not cast in stone or something. You can just say, well, I'm going to use 60-40, I'm going to use 50-50, maybe even 80-20. So long as you have a lot of data, so long as you have sufficient number of rows for training the model and sufficient number of representative rows to test the model, you're fine. Okay, so obviously we use the training data, and of course the machine goes into the training data, looks for patterns and figures out a model. Of course, once we have the model, we apply the model on the test partition, right? Of course, as you already know, the test partition was completely kept away. It played no role in the model building process. It's only playing a role in testing the model, evaluating the model. So we've got the test partition. We take this model that we arrived at from the training data, applied on the test partition, and out come the results on the test partition. Okay, so it is these results which are now going to tell us how good our model is, at least on the test partition, right? And if the model turns out to be good on the test partition, and if the test partition was properly created, then we would assume or expect that the model will also perform well on future data that we are going to see as the business goes forward. Okay, so how well did the model do depends upon the results that we get on the test partition. So to again make this even more concrete, this we understand that we build a model with the training data, apply it on the test partition and see the results. So concretely, it might look something like this. Let's say that this is a test partition of some data set. So we've already got the model based on the training partition. So here is our test partition. And of course, because the test partition is also historical data, the target attribute value is still available, right? Because we took our entire data set, let's say 10,000 rows. This is the 3,000 rows that we kept away. Now all of the 10,000 rows were historical data. So not only do we know information about the state and the age and the income and etc., all of the gender and marital status and education level, not only do we know all that, but we also know whether that corresponding person bought the product or not, whether the person was a buyer or non-buyer. That's already there because it's historical data, right? So we just partitioned some of it, put it away on the test partition, okay? But therefore, this is still available. So now what we can do is, since we have the model that we have built with the training data, we can apply the model on the test partition. Okay, so now what's going to happen is that when you apply the model is going to generate its own predictions for each of the rows. Okay, quite independent of what the actual status is for each of the rows, the model is going to make its predictions. Of course, for every row, the model is going to make its predictions based on all the predictor attributes. Okay, so ideally, I should have drawn this arrow starting from somewhere here to say that it's taking all the predictor attributes and based on that, it's calculating a prediction. Okay, now remember, this column is only a prediction that the model is making. It might be correct, it might be incorrect for a particular row. So in this example, for instance, you see that these three rows are examples where the model was actually incorrect. See, right? Here was a person who actually bought the product, but the model thought the person would not buy the product, so the model was wrong. Here is a person who did not buy the product, but the model prediction is that this person would have been a buyer. So once again, the model was wrong. Again, here is a person who's a buyer, but the model thought the person will not buy. It's wrong. So these are three situations in which the model was actually incorrect. Okay, so once again, as I've already pointed out, when you build these predictive models, don't expect that the predictive models are going to be super accurate. Remember, all we want is some sort of improvement over the status quo. Okay, so if the status quo is very bad, a model that is not as bad might still be quite profitable for the company. That's all we are looking at. Okay, so here's a case where we see that the model is making some mistakes, but the model is also quite successful in many other cases. Okay, maybe that has value. We don't know. It depends on the context. From your earlier course, you might recall that for classification models, the tool that we use to evaluate the model is called as the error matrix or the classification confusion matrix. Right? In the very first course, we had a small discussion about this, and we'll be getting into a lot more detail right now on that. Okay, so here you've got, from our test partition, the actual class that each of the cases belongs to. Okay, so for example, if we go back here, we are seeing this. This is the column that we are looking at. So you've got a bunch of predictor attributes, and here is the target attribute within the test partition, the actual class that each case belongs to. Okay, so that's what it is. And we see that this is from the test partition. There are 13 rows. It so happens that there are 6 buyers and 7 non-buyers out of the 13 rows. Okay, now from the previous slide, we saw that we applied the model to the test partition, and the model came out with its own predictions. And we saw, of course, that 3 of those predictions are actually wrong. Okay, so now, in order to give a quantitative estimate of the quality of the model, we create what is called as the error matrix. So this is a situation in which an actual buyer, this column represents the actual status, and this column represents the predicted status by the model, right? So this person was an actual buyer, but the model thought the person is going to be a non-buyer, right? So this is a case in which the model got a buyer incorrect. Here's a case in which the model got a non-buyer incorrect. The person is actually a non-buyer, but the model thought that the person would be a buyer. And here is again a case where the model got a buyer incorrect. Okay, so there are 2 types of mistakes that the model can make. Either it can say a buyer is a non-buyer, or alternately, it can classify a non-buyer as a buyer. Both of those are mistakes. Okay, so based on this information about the actual and the prediction, we create what is called as the error matrix, or also called sometimes as the classification confusion matrix. Okay, so we see that there are 6 buyers. Okay, so remember, the rows represent the actual scenario here, right? Because I've said actual. So this is going to represent the actual buyers, and this row is going to represent the actual non-buyers. Okay, and these are model predictions. So this column represents what the model predicted as a buyer, and this column represents what the model predicted as a non-buyer. Okay, so we are seeing that there are actually 6 buyers, and that is why the total of the first row is 6, right? Because actually there are 6 buyers. Okay, now we saw that the model got 2 of the buyers incorrect, which means what? Which means the model classified 4 actual buyers as buyers, right? Because remember, this is actual buyer, predicted buyer. 4 actual buyers were predicted by the model as buyers, and those 4 you can see here, right? This was a buyer the model predicted as a buyer 1. This is the second. that's the third, and that's the fourth. Okay, so 4 buyers were actually predicted as buyers, and 2 buyers were predicted as non-buyers. That's what we saw here, these two. Okay, now turning our attention to the actual non-buyers, we see that there are 7 non-buyers, but out of the 7 non-buyers, the model made a mistake on only one of them. This non-buyer was predicted as a buyer. All the other non-buyers were correctly predicted as non-buyers. Okay, so that's the 6 that's going here. 6 non-buyers were predicted correctly as non-buyers. 1 non-buyer was incorrectly predicted as a buyer. Similarly, 4 buyers were correctly predicted as buyers. 2 buyers were incorrectly predicted as non-buyers. This is what is called as the classification confusion matrix, or for short, error matrix. I will most likely use the term error matrix in most of my references to the term, to the object. Now that we have the error matrix, we can compute some statistics from that. I wouldn't call them statistics, some measures from that. Okay, so first thing, the easiest thing we can do, of course, is to get the counts of correct and incorrect predictions, right? So we know that this, here I'm considering a different classification confusion matrix with larger numbers, not the small numbers that we saw in the previous one, but you can see the process by which this might have been arrived at is pretty clear to you. So we have a total of 6,900 cases. That's just adding all of these, 5,000, 6,000, 6,800, 6,900. That's what we have here. And we know that in these cases, buyers were actually classified as buyers. And we know that these are cases where non-buyers were correctly classified as non-buyers. Okay, so these situations, the 6,000, 5,000 and the 1,000 represent, those counts represent the number of correct classifications performed by the model, right? So the model is correct in 6,000 of the 6,900 cases. Okay, so therefore, we can say the overall model performance is 6,000 divided by 6,900, or roughly 87%. Okay, and of course, we see that therefore the model is incorrect in 900 of the 6,900 cases. So roughly 13% of the time, which is what is left over, the model is incorrect. Okay, so the overall performance of the model is simply the total of the correct classifications divided by the total number of cases. It's quite obvious. Okay, but we can also look at, so we looked in this slide at the overall correctness and overall wrongness of the model, error rate. But we can also look at category specific performance, right? So after all, this is showing us the overall, on the whole, the model is correct 87% of the time. But we might be interested in saying, okay, that's all great, but how accurate is the model when it comes to predicting just buyers or just non-buyers? Meaning, how does the model perform for actual buyers and actual non-buyers? Okay, so that's what we mean by category specific performance. So here we see that there is a total of 1,100 buyers, out of which the model is wrong 100% of the 100 in 100 cases. Okay, so we know the overall performance is 6,000 divided by 6,900, or 87%. But looking at the performance on buyers, it is 1,000 correct out of 1,100 total. Okay, which is about 91%. And performance on non-buyers is 5,000 correct out of 5,800, which is an 86% performance of the model. Okay, so we see that the overall performance is 87%, but the performance in spotting buyers is actually slightly better than the performance in spotting non-buyers. That's just what the data shows us. We can also look at two other measures here. Right? We can say, well, if the model predicts that somebody is a buyer, how confident can I be in that prediction? Right? So here we looked at, if a person is an actual buyer, what is the chance that the model will predict him to be a buyer, or predict that person to be a buyer? If a person is an actual non-buyer, what is the likelihood that the person will be identified actually as a non-buyer or buyer? Right? Those two measures we saw earlier. But now we are seeing a different thing. We are saying, let's say that you've got a particular case and the model has said this case is classified as a buyer. Right? So we can look at how confident can we be of that prediction. Okay, so then we are looking at the column, right, of the 1800 predictions that the model made of buyers, right? 1800 of the 6900 cases, 1800 cases were predicted by the model to be buyers, of which 1000 were correct and 800 were incorrect. Okay, so this is the question we ask. If the model predicts somebody as a buyer, what is the chance of this prediction being correct? Okay, so that is going to be 1000 divided by 1800, or it's about 56%. Okay, that is because in general cases there would be a lot of non-buyers and very few buyers, right? So obviously when you have a model, out of the lots of non-buyers that the model has, it's going to that the data set has, the model is going to predict some of them to be buyers, but simply by the fact that there are so many non-buyers, the misclassifications of non-buyers as buyers in terms of actual numbers will tend to be quite large. Okay, so that's what we are seeing here, that if the model says somebody is a buyer, there is a 56% chance that this person will actually be a buyer. And there's a significant 44% chance that the person will not be a buyer, right? On the other hand, if the model says somebody is a non-buyer, what is the chance of that being correct? It's very high, right? It's 5000 by 5100. Okay, because there are very few classifications of of this situations in which this happens, right? So if the model says somebody is a non-buyer, the chance that that person is a buyer is quite low. So prediction of non-buyer is usually quite accurate. Now you will find that this is the case in general, right? You have one class which is of interest, which is identifying buyers or identifying fraudulent transactions or identifying people who will default on a loan. All of these are few and far between. Very few occur. These are the exceptional kind of occurrences, and therefore it's very difficult to identify the patterns that will that indicate these things, right? Whereas most of the people belong to the other class, and therefore predicting the other class is actually quite easy. So that is what you're seeing here. I'm not saying that this is always the case, but this is quite frequently the case. Now we could evaluate the performance of a model based on its overall accuracy. But when we do that, we are implicitly saying that all errors are created equal, right? Notice that these are situations where a buyer is classified as a non-buyer. These are situations in which a non-buyer is classified as a buyer. These are two different types of errors. Okay, now if we try and measure the performance of a model by its overall accuracy, then what we are effectively saying is both of these errors are equal. Okay, so the question we want to ask is, are all errors created equal? Okay, now notice that this error of classifying a buyer as a non-buyer could be a costly error, right? Because suppose somebody is an actual buyer. Let's say this is an automobile we are talking about. Then the dealership stands to make maybe a couple of $1,000 or more than $1,000 as a gain if they make the sale. Now if they take a buyer and classify them as a non-buyer, then they are effectively missing on a potential sale, and that could be a costly mistake. Whereas if you classify a non-buyer as a buyer, okay, that is likely to be much less costly. Now what would you do if you say a non-buyer is a buyer? Then you might spend a lot of sales effort on this person, right? Maybe spend some time returning their calls, calling them, maybe allowing them to test drive a vehicle, etc., etc. They take up your time in the dealership, but all of that may not add up to the same amount of money as classifying a buyer as a non-buyer, right? So the cost implications of the two types of errors could be quite different, and that is why when we look at a classification model, we usually don't evaluate the model only based on its total performance, right? We would like to go a little bit further, and that's what we are going to talk about now.